Here I will talk through the functionalisation, also known as passivation, of siliconoxide via a self-assembled monolayer. Here I will be using OTS or octadecyltrichlorosilane. The purpose of this passivation is to increase the conductivity of the resulting OFET, in our case to a range we can measure. I'll first explain the theory and then show the process of passivation. Do skip ahead if the practice is more of interest to you than the theory. The timestamp is roughly at the 3-minute 45-second mark. My understanding of how this works is largely based on electronic processes in organic semiconductors by A. Kohler and H. Bassler. It is possible I misunderstood parts, and do leave a comment below if you think corrections are necessary. Principally, there are 4 ways in which a self-assembled monolayer or SAM passivation increases the conductivity of an OFET. 1. It can reduce the effect of dipoles in the insulating substrate. 2. It can reduce the surface roughness. 3. It can alter the orientation of the deposited molecules. 4. It can prevent trap formation, particularly for OFETs in negative mode. I will begin by explaining the most complicated reason, that is the reduction in the effect of dipoles in the insulating substrate. My understanding is that OFETs conduct via a hopping mechanism, where charge carriers are generated via applying a gate potential. The charge carriers exist in a density of states, and in particular in the low-lying tail of it, i.e. tail states. From here, they must be thermally excited beyond a mobility edge in order to conduct. At this point, the states are able to delocalize over several states, allowing for conductance. A large density of states near the tail states aids in the conductance. That is, if the Gaussian density of states is narrow, this improves the conductivity. This is because it requires less energy to promote to the mobility edge, and further, delocalization is much easier when there is a high density of states. The delocalization of states occurs in space, and as such, close by states are easier to delocalize into. This may be thought of as due to the way a wave function exponentially decreases at the edge of a finite potential well. I do not have time to get into the quantum mechanics of a finite potential well, but the Wikipedia article is linked below. The closer the states are to one another, the more the subsequent states in the conduction band is able to catch this wave function, and hence allow conductance. So in summary, the density of states being narrower lowers the thermal barrier to conduction. The dipoles in the substrate, however, cause varied changes in energy via their electric field, and as such broaden the density of states. Adding a passivation layer reduces this effect. The improvement in conductivity can also be due to a reduction in roughness of the substrate. Of course, this depends on the substrate used and how rough it is. However, roughness can affect the way the substrate and the deposited dielectric interact, broadening the density of states. Additionally, orientation of molecules can change with passivation. The orientation of molecules can dramatically affect their conductivity. It has been observed in the literature that depositing onto OTS by, for example, P3HT dramatically changes the orientation of the deposited compound at the interface. This dramatically changes the conductivity. The final way in which passivation can help conductivity is by removing the native trap sites on the silicon oxide. This is particularly the case of OFETs which operate in the negative mode. Surface silicon hydroxide can be reduced in the negative mode to SiO-, and this traps charge and broadens the density of states to further reduce conductivity. Anyway, on with the passivation. OTS is notable for its hydrophobicity. Silicon oxide is quite hydrophilic, however. As such, a quick way to gauge the effectiveness of the passivation is to measure the contact angle of a drop of water before and after passivation. Here is before. Before passivating with OTS, it is first necessary to burn off organic impurities present on the surface. There are multiple ways to do this, but here I am using ozone cleaning. Ozone is toxic and produced by carcinogenic UVC light, so caution must be used here, as well as a ventilated fume cupboard. The light source used is linked below. The substrate is exposed to ozone for only 5 minutes. Subsequently, a 1 millimolar solution of OTS in dry toluene is added to the substrate, and it is left there for 20 minutes. The solution is then poured away and quenched with water before being disposed of. The substrates are then washed with hexane and finally thermally annealed at 150 Celsius for 5 minutes. Then the OTS functionalization is complete, the hydrophobicity is increased, and they work better as OFETs.